name is Alex, and I'm here to present software attacks on different type of system firmware, x86 and ARM. Before I will start, I want to say thank you, organizers of H3C, to having me here at my first time here. Uh, to some of you who may track what kind of research we published last years, you may notice that all of them, most all of them was x86 research related to the virtualization of firmware in x86. And then this year, we published first time some research on ARM and hypervisor exploitation for the ARM for some specific SoCs. And then there was before we will make that research, we were thinking about how we can apply vectors which we know from x86 systems to ARM system, because we read about different attacks and we see similarities. So that's supposed to be multiple different attacks which can be applicable for different architectures. And that was the motivation for this presentation. Basically, after we published a bunch of research for x86 firmware attacks, then we make an investigation for ARM firmware and hypervisor attacks. We were thinking about, let's combine this to one presentation and see like where is the similar methods, what kind of vector applicable just for x86, what kind of method applicable just for ARM, and so on. So during the presentation, I will switch from x86 to ARM multiple times. It will be confusing. I will try to make it less confusing, but basically the idea is it will be like blocks of x86, then blocks for ARM, and then back and forth multiple times, depends on the area which I will explain. So I will start just with introduction, really brief without details, just to making sure that we are in the same page of the terminology. Then I will go through some of the details about hardware configuration and how it's done in different platforms. Then it will be a bit about reverse engineering, and that part was interesting specific because before we have that research in ARM, we didn't have experience with ARM at all, and this is sort of will give you the idea how to start investigating new system which you never have investigated previously, some new architecture, where to start, what kind of method to use, and so on. So may be useful. Then attack vectors, again, which one applicable for different system, with some examples. So it will be example for x86, bypass Windows 10 VSM technology using some of the hardware interfaces. And for ARM, the result which is we published in Black Hat about exploitation hypervisor in some specific SoC. So x86. Typical system, we have user mode, we have kernel, then there is a hypervisor. Important point is that in x86 hypervisor is context switch technology, meaning that inside the hypervisor it also has the privileges level. And every time when you go in to the guest and coming back to the hypervisor, you're switching the context of entire CPU, and every guest has the structure which is contain all of the necessary data to that switch. Why it is important? Because this allows much more flexibility to the hypervisor technology and allowing the software use hypervisor for many different purposes, hypervisor privilege level or technology. So then we have the SMM and BIOS. SMM is basically system management mode, is the most privileged code in the system, which is basically a runtime part of the BIOS. So in x86 system, the BIOS has two parts. The boot time part and runtime part. Boot time part is basically the code which is running really begin after the system is on, and the runtime part of the BIOS is the part which is basically supporting some functionality during runtime. If there is any issue with the system, it's supposed to go and drop event to the SMM, and then SMM should handle this. And then we have the CPU peripheral and CPU peripheral, PCIe buses, and so on. In this presentation, there will be attack related to the hypervisor and attack related to the SMM and the BIOS. Then I already mentioned there is a boot time of the BIOS. What this means is, so when the system is powering on, the first instruction which is fetching is reset vector. The way how does it fetch work is pretty interesting, because at the moment when this instruction is fetching, There is no memory, no caches, nothing. But you need to somehow execute first instruction. So what happened is that when the CPU tried to fetch the reset vector always in a constant address. And then the transaction go into the memory controller. And the memory controller see the address and knew that this is the address of the reset vector. And it sent transaction to the PCH. PCH received the transaction and see, okay, this is the reset vector, and it redirected to the SPI controller. That's the way how does the reset vector work. When you have the instruction which is executing even without memory, without caches, without nothing. Then what happened next? There is a sec phase or first sort of first code which is basically running the system, which is make some basic initialization, for example, initialization of the TPM, initialization of cache, making cache using as memory, copy some other part of the boot part of the BIOS part of the code to the cache, and start executing the cache. And then it redirecting to PI phase. PI phase is basically pre-initialization phase. This phase is responsible for initializing necessary hardware to set the proper configuration of the security features and all of the necessary features which are supposed to be initialized for system booting correctly. So then it go into the Dixie phase. Dixie phase is one of the biggest phase in x86 BIOS during the boot time. That phase is responsible for initializing all of the protocols, all of the necessary components to support operation system services, because BIOS provides some of the services to the operation system, which is basically initialized in this phase. And then it go into the going and calling the loader of the operation system, and then the operation system is loading. The interesting part in the before Dixie, after Dixie and before operation system is exit boot services. That special event which is indicating that the boot part of the BIOS is done, and now the runtime the BIOS is supposed to be used, and boot part of the BIOS is not available anymore, like boot variables not available, boot services not available, and so on. That sort of switch when all of the security configuration should be set before the BIOS call exit boot services. So in ARM, it's a little bit different in perspective of the privileges level and in perspective of the boot flow. So in perspective of the privileges level, we have classical user mode and kernel, but then when we come to the hypervisor, there is slightly different, because hypervisor in ARM implemented as exception level or privilege level. So it's not a context switch technology. It doesn't have inside the hypervisor any other privileges level. It's just a privilege level. And it has the instruction which is triggering the code from the hypervisor. So meaning that hypervisor is less flexible, but in the other hand, it can be more isolated and configure it better in security purposes, because you don't need to care about that much stuff than in x86. There is no VMCS, nothing which is rely on context switch. There's just a privilege level. But as you remember, in x86 there was SMM, which was as a privilege level. In ARM there is a trust zone, and trust zone has a bunch of privileges level inside. So basically there is a trustless which is running in a EL0 exception level 0 for the inside the secure world, inside the trust zone world. There is the secure kernel which is running in a EL1 inside the trust zone world, and there is secure monitor. So basically, in the perspective of flexibility, the secure world much more flexible and has much more better capabilities than SMM. And how does this boundaries work? The boundary works in two things, isolation boundaries. There is one is memory isolation, which is done in the memory controller. So every time when transaction going from the normal world to secure world, or from secure world to secure world, it has the bit source and bit destination. And depends on the source of the transaction, it go press or not. For example, if the transaction going from normal world to secure world, the transaction will be dropped. So this is the way how does the isolation in the memory level work for the trust zone world. And also there is a hardware isolation, meaning that the interrupts working in a way that all of the interrupts from the normal world can be delivered by a specific way to the secure world. There is no mechanism how the normal world can trigger any other code except the specific exception vectors, which I will explain later. So compared to x86, the difference is that hypervisor is working as a privilege level, and the trust zone world working as an entire technology which has a bunch of privileges level inside. So if we will, yeah, I have the slides for that. I will come back to that. So now, if we will talk a bit about boot flow in ARM SoCs. So first of all, for ARM SoCs is all specific for specific SoC. So it's not like a standard way which is always working this way, because every vendor may implement their own way to boot the SoC. Because ARM SoC, it is more isolated system because you have the system is tied to a specific operation system, and there is sort of all of the devices is mapped directly to the to the physical address spaces. There's less flexibility, and because of that, the boot flow can be defined by vendor differently. And this is one is for Snapdragon 810, so it can be different for Samsung, for example, or for iPhones. So everything starts from RPM, Resource Power Management Unit. So that unit basically running even before the main CPU starts. So then the RPM is initializing the main CPU, main application CPU, and triggering the code from the ROM part of the main CPU, which is basically the memory into the CPU ROM somewhere. So it's not accessible for software at all. You cannot read it, you cannot dump it, you cannot verify how does it work. They're just there, and it's doing some things for initialize the hardware and for verifying next step of the boot flow. And next step of the boot flow is SBL, secondary bootloader, which is basically first part of the code which is accessible from the software. This is basically the code which is making the initialization of the first trust zone monitor privilege level and some of the memory and so on. So if you will see that the left side is just read-only memory, meaning that any vulnerability in that part will be not really easy to fix because that memory is controlled by vendor and it's not accessible for software at all. Any part, any vulnerability in the read-write part can be updatable, and when update will be delivered, the read-only memory verify read-write memory and checking the signature read-write memory before it trigger the code in read-write memory. So then SBL will continue calling the trust zone monitor, which is responsible to initialize and set all of the protection for the trust zone. So after this point, after the trust zone monitor initialized trust zone kernel and applications, the trust zone is locked and not modifiable. So if there was any possibility to create a DMA attack during the boot time, it's supposed to be done during the SBL or trust zone monitor phase. Then after trust zone kernel, there is low chances that the configuration will not be set. So, and then this is all done for initializing secure world or trust zone. And then the first code, which is untrusted code, which is running in the system, is the hypervisor. So basically, the trust zone monitor, actually trust zone kernel, will trigger the hypervisor code to continue the boot flow, and then the hypervisor will initialize the operation system, and so on and so forth. That's the boot sequence for the ARM. As you can see, it's look like they have more phases than x86, but in reality there's less phases. They are more straight, and because the platform itself doesn't need that much initialization, because in SoC compared to the core technology, there is a bunch of stuff which is constant, and you don't need to configure them. That's why there's basically, I would say, two phases. One is read-only, which is some code which verify in read-write part, and there is just a couple phases in read-write, which is much more simpler than x86, and I will have example why. So anyway, we start talking about different architecture, and there is sort of summary what I was mentioning from the beginning of the presentation. So first of all, root of trust. As I already mentioned, the root of trust for ARM is pretty restricted and rely on the OEM configuration, OEM fuses. So if the OEM want to lock the phones or any ARM system, they just program the fuses, and then the system will just support the boot flow from the read-only memory to the operating system with specific vendor signature. So there is no one can just put the binary there during the boot flow. If the vendor is not locking the phone, then meaning that you can reset the fuses, and after some point you can load your own operation system, root your phone, and run tests which you want. But that's supposed to be supported by OEM. If OEM not supported this, then there is one way to do that is find vulnerability in trust zone. Trust zone has accesses to the fuse, and then you override the fuses. That's the way how does jailbreak works and unlock some phones is working. So for x86, root of trust was more flexible because you can run any operation system. You can run a bunch of different software, and there was no real root of trust except secure boot. But secure boot was sort of software way which is relying on integrity of the BIOS. So if BIOS was compromised, and then you can bypass secure boot and the rest of the boot flow. There was a new technology from Haswell called it BootGuard, which is make it much more better. So it is close to what ARM is doing because the root of trust is in a ROM memory, which is controlled by the platform vendor, meaning Intel. But that one required that OEM who is using the technology is supposed to use this technology correctly, meaning that they need to program fuses, need to lock the technology. If there is just enable technology and not locking the technology or enabling it not properly, then it is definitely an issue and can be used to bypass the entire boot flow and compromise the root of trust, the process of the boot and like all of the technology which is relying on that. So about TE, trusted execution environment. As I already mentioned, the ARM has really good flexibility in a trust zone. There is a privileges level, which is, I would say, in the perspective of technology, similar what is virtualization in x86 doing. And because x86 virtualization also has privileges level and separation between them. So that's why in Windows 10, the VSM virtualization-based technology was build it based on virtualization, not based, for example, on SMM or something else, because there was enough flexibility to build a technology on the top of virtualization. And you cannot do that in ARM, because in ARM there's working as a privilege level. So that's sort of the brief idea why this is important at all. When we built our attack for x86, we will use that flexibility, which is virtualization technology provide to compromise the hypervisor in a Windows 10. And for ARM, there is a bunch of vectors which is really similar will be for the trust zone, which we will apply to the virtualization. Anyway, let's go and talk a bit about the hardware interfaces. So for x86 hardware interfaces, I split it for two categories, is CPU interfaces and SoC interfaces. In the CPU perspective, there is a CPU state, obviously some general purpose registers and other stuff, and there is also MSR, model specific register. It's basically some register which is storing configuration in x86 system. And sometimes it's even working as a control registers when you write something and you trigger some action. That basically allowing the vendor creating a bunch of features and communicating to that features using that registers. And the software has the instruction to access that register, to read and write to that registers. In the perspective of SoC, there is a bunch of interfaces, I/O, PCIe, and so on. The one of the interesting for us for today will be memory mapped I/O, memory map MMIO interface. It basically the interface which is allowing to talk to the PCIe devices through memory. So every transaction to the MMIO of the device will go in directly to the device through the memory controller and PCH. So if we will run if we will enumerate all of the MMIO bars, MMIO bar is basically the register which is defined in MMIO range. We will find a bunch of ranges. That ranges is represent some of the device in the system. Uh, we, we created that tool which is basically doing this enumeration, so you can run this tool, which I will use basically all over this presentation. This tool is basically doing a lot of accesses to the hardware, including the accesses to the MMIO of the devices. And as we will see later, there will be a different in implementation of the MMIO for ARM and x86. And one of them will be used for attack for one of the attack scenarios. So in ARM there is a little bit different. So you have the general purpose registers and some of the special control registers. Also you have the registers inside the core processors, and that registers is accessible through the specific instruction. It's really similar to what is MSR is mean for x86, except this interface is covering much more registers from much more different units. So I would say that all of the necessary core interfaces accessible through that interface. In the perspective of the SoC, there is also less interfaces than x86 because MMIO in ARM is a constant addresses list. Because in SoC you don't need to have relocatable MMIO ranges, because in SoC the purpose for SoC is make everything on chip, which is meaning that everything will be on one die or in one chip. And in this case, if there is device, that device has the MMIO address, and that address always constant. And even if there is any PCIe device which is implemented in ARM, they will be implemented through MMIO. Basically, there will be the PCI controller which will have the constant address, and then there will be the MMIO of that PCIe device, which will be defined in that PCIe controller through MMIO. Anyway, the main idea is in ARM there is less flexibility because the SoC don't need the flexibility, and because of that there is less attack vectors. So that is the example of what's going on exactly. So that's in the right side we see there is a list of the MMIO ranges for the devices, and that list is always the same. So if you reboot the system, if you take another SoC, this specific SoC, you will see always the same list of the addresses for all of the devices. What this means that they're not relocatable. They're all constant, and basically because they're not relocatable, there is no source for attack. And then what we like to do with these MMIO ranges? So we want to investigate and see how many of this register is accessible. So we may just create a simple tool which will just read and write these registers. And depends on that, we may figure out multiple different things. For example, if we read it from the different timestamp, like after the system just booted and then later on, we'll figure out that there are some registers may be accessible right after boot, but not accessible in the runtime. What is telling to us? They're telling that there is two different phases for SoC to boot. There is a boot time phase and runtime phase. Really similar for x86, but the difference is it's not documented. So we don't know how does exactly this work because there is no documentation which explains these two phases. We just by experiment can figure out this. And another interesting part is it can be used for attack because if there is any register which is supposed to be locked but it's accessible after the system is boot, it may be used to some of the attack scenario when you, for example, this register is contain the address, and then you use this address to overlap with more privileged code. So that is one thing. Another thing is you may read the register from different privileges modes, say from hypervisor and from the kernel, and see how many of them will be accessible. Anyway, you can make a bunch of different things to understand how does that MMIO work. And in some case, you may figure out that there is some security issues. For example, if you figure out that one of the device supposed to be trusted, meaning just accessible from the trust zone, but it's accessible from the normal world. That's sort of issue which may cause some problem for the system. And the interesting part is that it's not really easy to find documentation from the SoC and from all of the MMIO of the devices. If you think about that, the ARM is not providing the description of all of the SoC because it is vendor specific. But vendor doesn't provide this as well. So in some of the, so to find the documentation, you may want, there's one way. You need to sign for program which will ship to you the developer boards. And when you get the developer boards, you will figure out that the developer boards has also documentation with the description of the registers. And then you can map which of the developer boards represent which of the SoC for the phones. For example, I've bought from Nexus 5X and 6P developer boards, and then when I figure out all of the MMIO from the devices. But interestingly, that it's not really accessible, so you cannot just Google it and find the description of this. The consequences of that, it can be two things. First of all, we cannot verify if it's configured properly or not. And second is, we don't know exactly what is going on in the system. So say when I make an investigation in the Google Pixel, I figure out that the system has more than 10 different firmwares. And the interfaces for the firmwares is different. Some of them is SPI, some of them I2C, and so on. But there is no documentation whatsoever when you can find all of the description for that interfaces, how does they work, registers, and so on. That was sort of interesting point, and experimenting with the MMIO of the devices may give you some ideas about what the device is doing. Anyway, let's come back to x86. We already got the idea that x86 has a much more complicated boot process because it allows better flexibility and so on. So because of that, x86 is reconfigurable, meaning that there is a bunch of things can be configured differently, including security configuration. And over the years, we collected different vulnerabilities found by different people, including us, in the different interfaces of the firmware, including configuration of the firmware. And this is the list of all of the vulnerability which we found by 2015 in x86 firmware. Most of them is configuration. Like some of the registers supposed to be locked, but they're not locked. And because they're not locked, there is some accesses to some of the region which is not supposed to be. And if you think about that, there is like more than like 15 of them, different vulnerabilities which were found. It's fine. It is fine because the system is super flexible and allowing you a lot of reconfiguration. The vendor just needs to take care of all of this and making sure that the configuration is set. That was supposed to be done. Then 4 years later, in 2017, we made the analysis to check one of that vulnerability which we disclosed it in 2013, how many systems still vulnerable to this vulnerability. And we were surprised that even in 2017, for some of the really common type of vulnerability, which is allowing you direct access to the BIOS region in a SPI controller, there is 500 different modules, laptops and desktops, still vulnerable to this vulnerability. So we started talking about this vulnerability in 2013. And then, even in this year, we still have a bunch of systems which is vulnerable. There's the vendors is coming a little bit better because some of the vendors is making progress. If you will see, like Dell, they have just 11 systems which is still vulnerable, which is not bad because they have thousands of systems, and they may not just update that 11 because there was legacy or old system. So they are making really good progress. But some of the vendors still have a bunch of systems, even modern system. I bought recently some of the Lenovo, I don't remember which of the Lenovo, but latest one from this year, Broadwell one. And that's still vulnerable to the classical vulnerability, which is allowing to get the access to the firmware. So that's sort of things which we need to think about. So in ARM, there's a little bit different story. As I already mentioned, first of all, SoC is not documented. So we don't know really what's supposed to be set, what the security configuration need to be set. We don't know how to check it. We know some things. We know, like, say, bootloader supposed to load just silent binary. We know, like, basic stuff for the boot flow. And one of the basic stuff is the fuses. So we definitely need to check that the fuses is programmed and locked correctly. That's something which we know about the boot flow and the security protection of the boot flow. Also, we know that when the trust zone initialization going, there is some register which is supposed to be set in the core perspective. That's something which we also know, but we don't know what exactly in perspective of SOC is supposed to be set to log the firmware accesses to the interfaces of the firmware, different firmwares. And what I noticed is when I bought that developer board and I have that spec from like many thousand pages, I start to read register from that pages. And I figure out that a bunch of that register has some hidden sort of lock configuration. Basically, the register is telling that this register is rely on lock to another register. And the another register is rely on some other locks. And what this means is, this mean is that in SOC there is also a bunch of register which is supposed to be set to make the platform fully protected and locked. But the point is, this data is not really accessible easy, because to find this, it's not publicly available. You need to go through some special process. And what this means for us, it's meaning that we buy a system, we buy phones and other devices, ARM-based devices, and we don't know, does they properly set it or not? Because we don't have the good tests for these registers, we don't have the information about this at all. So we need to just sort of trust vendor that vendor is doing the job well. If you not trust vendor, then there is not easy way to. I've tried to do that, but I figure out there's so many registers to which I need to count to. So I finally didn't manage how make it automatically to check all of the registers in the system. And the one thing was really important, that some of the register, I found that they are not locked. So they're supposed to be locked, they're not locked. I didn't figure out the security impact of that registers, but the register which is supposed to be locked by the spec is not locked. It's not really a big problem unless there is impact of this. And for some registers, maybe impact of that. So how we can start reverse engineering of the firmware, because we already talked a bit about interfaces, about boot flow, about the configuration, so on, but we want to go in deep and see what is inside the firmware. In x86, there is pretty easy to dump the firmware interface, dump the firmware through the SPI interface, and there is a command in chipsec. You can just call chipsec-util SPI dump, and you dump the firmware. Then you can decode the firmware and extract all of the components from the firmware, and then you can analyze every of that components one by one during the IDA, or make some automation using some of the UEFI runner tools. There is a bunch of research done right now about how does it work, from Dmitry Oleksandr, from other people, from Snare. I will not stop too much here, but basically, if you want to start analysis of the system from an x86 system, you just need to dump them, decode, and analyze the binaries which you find. And the binary which you find, it will be just regular x86 PI files. So analysis of the BIOS in x86 firmware is really similar just for analysis any other binary, NTDLL or whatever binary you want. So I will focus here a bit on how can you how can you start reverse engineering and analyzing ARM systems. First of all, because it was pretty interesting when we did this, and another is it's sort of one of the first presentation for the 64-bit trust zone analysis. So it may be interesting as a methodology and as a result as well. So to start analysis of the trust zone, you need to find the binaries. And there is two ways to do that. One was to dump the firmware from the system. But the point is, again, there is one interface which is accessible. And that interface was working until recently. And that interface is allowing you to dump the firmware from the system. But then later on, that interface was disabled, so you cannot do this anymore. So, but how can you find the firmware? Another way to do that is find the factory image from the vendor, basically images which is using to restore the system from the original state, from the state which was supposed to be after manufacturing. And then in the factory image, you can extract the bootloader, which will contain all of the binaries, including trust zone binary, including hypervisor binary, including some of the SBL, a secondary bootloader binary, and you can start going and analyze them. For example, if you want to analyze hypervisor and see how does hypervisor work and so on. One another important thing is the hypervisor in that specific SoC was enabled like recently from generation of Snapdragon 808. It is basically the time of Nexus 5X. So anyway, you take the trust zone binary, you load that in the IDA, and you will see there's a bunch of sections. Some of them is represent trust zone kernel, some of them is represent trust zone monitor. So basically you have entire code of trust zone kernel or trust zone monitor. From here you can start reverse engineering and analyzing the functions, the entry points, and so on. Also, you want to have the dynamic environment to run the tests, and especially if you have a phone. For dynamic environment, you need to root your phone and rebuild the kernel to allow and load the drivers. And then with that, you can load any drivers to read physical memory, to read the memory of the devices, and so on and so forth. And there is a bunch of tools which is already doing this. So there is a matter of time just to compile the kernel and to compile these tools. And then from here, you can run this and analyze the system. Now, after you load the binaries, the trust zone binaries to IDA, and you have the dynamic environment, you need to start looking on interfaces. Where is the entry point? How does the calling convention working? How does the argument passing from the normal world to trust zone world? One of the things which you can go and take a look is open source implementation of the trust zone. It will give you a lot of information about how does handler works, what the security configuration is supposed to be set, and where is the sanity checks for different conditions. That was really useful to understand, especially one thing which was entry point to the vector table, which is basically the main code which is running whenever any exception happen in low privileged code. So that was mentioned right now, that vector table. So first of all, how we can find the vector table? The pointer to the vector table should be stored in vbar EL3 for the secure monitor. So if you find somewhere in the code that someone set or read that register, and you will find the constant, the address of that table, then from here you know the entry point to this privileges level. So from here you can find all of the handler from SMC. SMC is the event which is going from the normal world to secure world. And from there you can analyze the entire flow and find where is the input buffer handler set, how does it work, and find some software vulnerabilities there. So here is the example of that vector table, and here is the SMC handler. SMC handler is basically one of the main interfaces to the trust zone, and this interface is often used to compromise the trust zone itself. The secure monitor in the trust zone, it's doing just one thing. It's redirecting request from the normal world to secure world. And then someone need to handle that request. And there is the trust zone kernel doing this. So trust zone kernel has something which is called SMC services, which is handling the specific request from the normal world. And when the normal world trigger this request, it go into secure monitor, and then secure monitor know where exactly to call secure kernel, and it will call secure kernel, and then secure kernel will handle it, will figure out which of the SMC handler it want to call, and then call them. So there's supposed to be a calling convention between the normal one and secure world, because if there's any services in trust zone, like say you want to get the random number from random number generator. In ARM SoC, it's not that trivial. There is no instruction which is giving you this. There is a random number generator device, but that device accessible just from trust zone. So if you want to get the random number, you need to send a request to the trust zone. The trust zone will talk to the device and will provide you that number back to the normal world. But you need to know the calling convention between normal world and secure world. There's two ways to do that. You may want to make a reverse engineering and figure out how does the arguments is passing, or you can just take a look at open source implementation of the trust zone drivers, which is basically implementing this interface, and you will see how does the arguments pass in there. And the calling convention working like this. If you have less than 5 arguments, they will pass in from the general purpose register. If you have more than 5 arguments, they pass in through general purpose register and the buffer. Why it is important? Because we need to understand how does it work for the attack purposes, because we want to build the Pfizer, we want to fuzz this interface and find the software vulnerabilities inside the SMC handlers. So this is the SMC default handler, which is basically checking the arguments and calling the specific SMC handler to manage the services. The interesting part, how does it work? That SMC default handler has a bunch of sanity checks. And one of the checks is basically checking that the arguments which you pass in is not addresses which is overlapping with trust zone. So basically, it assuming that first argument is address and second argument is size. And it's slicing through arguments to making sure that they are not overlapping with trust zone memory. That is really smart check, because if you will compare with x86, in SMM implementation, the default SMM handler doesn't have any sanity checks at all. So we just pass in arguments to specific SMC handler, which is making code less secure. But in ARM SoC, and specifically in Qualcomm implementation of trust zone, this sanity checks is pretty smart. So then I already mentioned there is SMC services, which is a normal word can call. That SMC service is stored in a table, and you can find that table in a binary, and then from there you can reverse engineer every of the services one by one. And this is the example of one of the services. The interesting part of this is that if there will be no that checks, there is a write primitive. So this handler takes 3 arguments, it calling subroutine, and subroutine making a write to one of that arguments. So in the case if the system doesn't have that checks which I shown previously, it will be definitely vulnerability. But because they have that really good sanity checks in the beginning of the SMC flow, that this code is not vulnerable. It's working fully without any problems. But it still have a write primitive. You just can override anything outside of the trust zone. Everything which is not protected, you can override by using this SMC handler, which we'll use later to compromise hypervisor. Another really interesting part and a really important trick is, as I already mentioned, the SoC is the constant address, MMIO of the devices is the constant addresses in the ARM SoC. Because of that, you can find the addresses of the specific device, and then you can restore what exactly this SMC handler is doing based on information from the device. So you kind of increase your knowledge based on understanding of the addresses which is using as a constant inside the SMC handlers. Another important trick which will help you to build analysis in the trust zone is error code. So different flow has different error code. And when you send input to the SMC handler, you can basically, depends on the error code, figure out what kind of flow you execute. And depends on that, you may see the coverage, you may adjust your input, you can find the better coverage. Unfortunately, there is not a unique error code for each flow. So some flow has the unique error code, some of them is not, but it's still useful information. Anyway, and the last point which will help us to run tests and Pfizers and analyze the system is the reverse engineering of the hypervisor. The idea is pretty much the same. We need to find the reset vector, and we need to find vector table, and we need to find the configuration of the hypervisor in a binary. After we find this, we can restore what exactly hypervisor said, what paging it used, what kind of translation, and so on. That is example, for example, TTBR-EL1 is the register which is showing us the stage 1 translation table entry. From here, we can restore all of the stage 1 translation. Stage 1 is like similar to, in x86, we have 2 levels of translation. From the guest virtual address to the guest physical address, and from guest physical address to the host physical address. Here the same, but it just call in stage 1 and stage 2. Stage 1 is from the guest virtual address to, they call it intermediate physical address, and then from intermediate physical address to the host physical address is stage 2. So anyway, we already know details about something about hypervisor, something about trust zone, but now we need to go and take a look deeply on the attack vectors. And we start with x86. Runtime attack vectors is pretty straightforward. You want to compromise the SMM code from the hypervisor or from the kernel, or you want to compromise kernel, or you want to compromise hypervisor from the kernel, or you want to compromise from the kernel SMM and then redirect the attack to the hypervisor. So there's two main classes of the attack surface. One is hardware configuration. Remember when I showed you the 15 different vulnerabilities which was found previously? I call it hardware configuration because it's basically setting some registers. And another one is SMI handlers. SMI handlers is really similar what is SMC handler in ARM is. It's basically supporting some services which is necessary to have in a platform. And if you will see in ARM, there is a little bit different story because ARM has more privileges level in the secure world. There is much more vectors attack is here. And because it creates a lot of flexibility, it also creates new vectors of attack. For example, trustlets. Trustlets is the trusted application which is part of the entire secure world. So if somehow you can compromise trustlets, then you can build attack inside the secure world, which is completely ARM-specific use cases. There is no analogy in x86. And there was interesting research published this year, which basically allowing you to load the vulnerable trustlet inside the secure world. What this allows you to do as an attacker, when to release the update for the trustlet, you take this update for the trustlet, you take the vulnerable trustlet, you load the vulnerable trustlet to the secure world, and then you can compromise now that vulnerable trustlet from the normal world, and then you can build the attack from the trustlet to compromise entire secure world. And interestingly, that these attacks is not really well investigated because there is no good methods how you can make an investigation of the secure world if you compromise already trustlet. What I mean about that, if you analyze secure kernel, mostly they try to make a checks from the input which is coming from the normal world. But there is not well tested the interface from the trustlet to the secure kernel. And even in IDA, with the simple analysis, you can find the buffer overflow vulnerabilities from trustlet to secure kernel. And interestingly, that if you compromise secure kernel, there is no need to compromise secure monitor because secure kernel already have access to all of the devices. So basically, even with all of this flexibility, it still has a bunch of issues related to the architecture, and specifically because there is not too many tools to validate the interface between trustlet and secure kernel. Really interesting to research. So one of the attack which I will fly really fast, which is applicable for both architecture, is DMA attack. Pre-boot attack when you inject some of the boot component during the boot and you can own the system. This attack is applicable for both systems. And in x86, there is a couple different scenarios for this attack as well. One of them is if you want to use the DMA attack without any external device, there is also integrated graphic device which has DMA capability. So if you build in the attack and you need DMA capability, you can use just the graphic DMA to run it. And for ARM, it's basically completely the same, but for ARM, I didn't find any integrated DMA capability. So if you want to run DMA attack, you need to have external device. Now, poison pointer bugs. We call it like this. The vector is applicable for both architectures. The vector is applicable for both architectures. The main idea is you pass untrusted buffer from low privilege level for high privilege level, and you pass the address of the high privilege level. And then if this is, do you have any question? Excuse me. Do you have any question? Okay. Yeah. So in x86 system, that vector was investigated a lot. And in EDK2, there is a COM buffer which is interfaced to the SMM code, and there is an EDK1 general purpose register is interfaced to the SMM code. was a bunch of research about that. The main idea is if the attacker controlling the address just overlapping with the SMM code, then it will allow to have a write primitive, which is basically, in many cases, making privilege escalation to the SMM. There is a reference to the work, if someone wants to get it more deeply. What happened next? If there is hypervisor, if there is SMM code is vendor making a fix which will check that the pointer is not overlapping with SMM, it's still not fixing fully the problem. Because in this case, attacker can find something else and point the pointer to that sensitive piece of thing and make the right primitive to there. And you may ask what that sensitive thing is. And in x86, it can be hypervisor, for example, because SMM code doesn't know the layout of the hypervisor and guest. And in this case, if you point in the pointer of the if you point in the address of the hypervisor to the SMM doesn't check it, it just write it there. So in this case, if there is any guest has access to the SMI interface, can trigger SMI event, it may override the hypervisor without even having any issue in the firmware itself. So in x86, there was a really good investigated vector. And then in ARM, there is really similar vector for the trust zone runtime interface, SMC. So SMC, as I already mentioned, has also interface as a general purpose register. When you pass arguments through that, and for example, if the SMC handler is supposed to write output buffer, you pass the address of that output buffer through general purpose register. Exactly the same scenario as in x86. And there was bugs which found previously in this specific vector a couple times in 2014 and 15. We created Pfizer to check this vulnerability, and in Nexus 5X, 6P, and Pixel, there is really good sanity checks, so that vector is not really easy to find vulnerability in. Then another vector in ARM was the double fetch or race condition. So if you pass in the big buffer as an argument to the SMC handler, and if this buffer is stored in the memory, then there can be a case when this buffer can be modified by another CPU. And this is really interesting vector because in x86, this vector is not applicable at all. Because when you call in the SMI in the x86 system, the SMI is waiting until all of the cores will go into SMM. So this vector is almost not applicable to x86. But in ARM, that's really a really good vector because you can find by static analysis the buffer which is passing from the normal world to secure world and figure out is there any window between between checking and using that buffer. Another vector which is also applicable just for ARM is confused deputy attack when you pass in the address of the trusted device as in a general purpose register. As I already mentioned, there is two types of device, trusted and untrusted. Trusted device is device which is just accessible for the secure world or for trust zone. They're not accessible for the normal world. But what attacker can do, because attacker knows the address of that secure device, it can pass the address of that device as an argument and ask SMC handler to overwrite, to make a write to that device. Really interesting vector, but unfortunately we are on the Pfizer and they have sanity checks for this as well. Google Pixel actually has really good firmware. That's why this vector is not applicable as well. But really good vector may be applicable for different other SoCs and different systems. Another vector which is really interesting, but it's more applicable for the x86. As I already mentioned, about MMIO of different devices and the difference between x86 and ARM. So one more quick recap. You have a MMIO range, which is basically transaction to that range will go directly to the device. And every time when operation system or someone else want to talk to the device, they're talking through the MMIO range. But in x86, MMIO ranges for PCIe devices is reallocatable. And the address for this range is stored in MMIO bar inside the PCIe config space of this device. So basically, operation system has capability, or any malicious driver has capability to overlap MMIO range to any other location in the memory. if the MMIO bar is not locked. But in many cases, MMIO bar is not locked because they allow in operation system relocating the bars for increase the flexibility of the system, because it's not SOC. In SOC, you need to have a constant, but here you don't. Anyway, because of this, attacker may overlap this MMIO bar with the SMM and build attack on the top of this. So when the transaction going from the device or to the device, in this case, it will not pass through because of the TSEC protection. But SMM itself has a bunch of SMM handlers which is reading and writing to the devices. And because of that, when you overlap the MMIO bar with the MMIO range with the SMM and trigger SMIs, some of the SMIs may read or write to the SMM. So basically, you have sort of write primitive to SMM. Really interesting attack for two reasons. One is the concept is really applicable to anywhere. So every time when you see the register which contain the address, you always can overlap it with more privileges level and see how does memory controller handle this transaction. Another interesting part of this attack, because in x86 system it can be really applicable. For example, spy bar, which is relocatable spy and not lockable, you have really good control of this bar, and you have really good control of the data which is using to this bar. So with this bar, you have really great write primitive which you can use to make a privilege escalation to the SMM code. And in ARM, we can try to apply the same methodology. We can try to find the registers, overlap with trust on memory, and see how does the memory controller handle it. But because we don't know all of the registers which contain the addresses, because we don't know all of the layout of the SoC, it's not really easy to apply this vector with all of the variation of this vector to the ARM system. Now we come into the first sort of attack which was done in x86 system to the Windows 10. So Windows 10 has the technology VBS, Virtualization Based Security, or VBS is also sometimes called VSM, Virtualization Security, something. So the idea of that technology is Windows 10, you can enable the hypervisor, and the hypervisor will create the secure VM, which is a really trusted small VM. And inside that secure VM, there will be some secrets, like credentials of the domain or something like this. And the idea is, if the attacker will compromise normal world and compromise just a system which user use, then it will not find that credentials. It will not find the domain credentials. The idea is really awesome. And the way how they think about this technology is really great, because you have the virtualization technology. Why not use this technology to make an isolated container? The idea is really great. The issue is implementation, because the normal world has all of the accesses to the firmware interfaces. It has accesses to the MMIO bars. It has accesses to the SMI handlers. It has accesses to S3 boot script. So any attack through the firmware can compromise hypervisor and the secure VM. And especially the one which I explained it previously, the SMI pointer, the MMIO bar overlap, all of them is applicable. But even if there is no issue in the firmware itself, there still can be, the firmware can be used as a confused deputy attack to the compromised hypervisor. Because again, as I already mentioned a couple of times, SMM doesn't know the layout of the hypervisor and the VMs. And if you have access to the SMI handler interface, and the normal world has the access to that interface, then you can trigger the SMI with the address of the hypervisor and override the hypervisor. And that was an attack demonstrated in a couple of years ago. Interestingly, that Microsoft released an update. What they mention is they created a CPI table, which is basically having the this table is represent where is the buffer supposed to be for the output for the SMI handlers. What this means is that this table is basically a sort of calling convention between the operation system, the hypervisor, and the firmware, where is the buffer supposed to be. And this is really good. It's preventing the SMI poison pointer attacks. But it's not preventing other attacks. For example, attacks when you can overlap the MMIO bar, this one is not preventing. So that's just as a partial fix. And another point is, this is just a spec. Now all of the vendors, all of the BIOS vendor need to apply this fix and deliver the BIOS updates to all of the system. Then it will be fixed. But the spec is just explaining how it's supposed to be fixed. Now let's come in back to the ARM. So we got a lot of knowledge about x86, about flexibility of the hardware configuration, different attack vectors, so on. And as I mentioned, then not all of the, almost all of the vectors which we tested previously, not applicable to ARM. For some reason, because they have sanity checks or architecture is not fit or something like this. Then we start thinking about, okay, we want to investigate a little bit the hypervisor. And that was really interesting because we want, okay, let's find the hypervisor in the memory in ARM system. There was a Snapdragon 810. It basically Google Nexus 6P. Then we find the hypervisor in memory. We get the address of the hypervisor. We use the address in SMC handler, and then we override the hypervisor using this. And we was asking, why? Why did it happen in the first place? And then we start thinking about this more. And one of the things which we asked ourselves, why we even find the hypervisor in the memory? Because if you think about that, we're running our tool from the kernel, and kernel not supposed to have the access to the hypervisor. And we were thinking, okay, maybe this is some old copy, some legacy copy of the hypervisor, which was not real one. Then we write to the hypervisor, and the system was rebooting, so that was really hypervisor. So in the Snapdragon 808 and 810 SoCs, the hypervisor is accessible from the kernel. And this means all of the phone with generation of this, like Nexus 5X and 6P, is vulnerable to this vulnerability. What this vulnerability allows us to do? So because we have the read-write primitive to the hypervisor, we can make a privilege escalation, which we will demonstrate later. And also we were thinking about why, in the first place, when we read the hypervisor from the original address, we read the real hypervisor. Because if there will be a second level of translation, the address is supposed to be different. And we make an assumption that the second stage of the translation is disabled. And then we confirm it later. So then we build the attack scenario like this. So from the malicious kernel, from the malicious driver, we compromise the hypervisor. We lock down hypervisor, so now the hypervisor is not accessible as it was. And then we backdoor the hypervisor in a way that malicious application can talk to the hypervisor through memory and ask accesses to the kernel from that interface. To doing this, we need to somehow patch the hypervisor because we have a read primitive, but it's not code execution. But remember when I mentioned that vector table is the entry point to all of the exception coming from a low privileges level. So in vector table, there is some entry which is calling periodically. Like periodically, every couple seconds, this interface will call this handler. And we just find this handler and we'll patch the handler with our shellcode. So we put our shellcode right in the end of the function of the handler which is periodically calling. Then what we designed protocol between application and hypervisor. So if application will store some magic number, then we know that after this magic number there is a command which is supposed to be running in a hypervisor. So now we run an exploit. Exploit basically find that hypervisor is open from the kernel. It patching the vector table. Then it checking that the shellcode is stored there, and then it just leaving like as is. Then we run our application, and application basically storing the command which basically asking to read the kernel memory from that command buffer. And then the hypervisor is scanning memory periodically because it's calling periodically because the patch itself is calling a couple times in a second. And then it finds this magic number and know that after the magic number I have a command, and then it executes the command. What this demo is about? Then you can patch the hypervisor and runtime. You can log that and backdoor it in the way you want. in the two specific generation of SoC with Snapdragon 808 and 810. So then we reported this bug, and then as a result, we got the response that this behavior is not exist anymore in next generation. So if you got the next Snapdragon 821, which is basically a Google Pixel, that behavior is not there. So meaning that in a Google Pixel, they are making good separation level between the kernel and the hypervisor, and then this vector is not applicable anymore. And then it's not applicable through SMI handlers, through SMC handlers as well. So if you pass the address of the hypervisor to the SMC handler, it will have the proper check. As a result, there is still two generations of the phone which is vulnerable to this vulnerability, which is not fixed at all. And the fix was just in the next release. They just changed architecture. Anyway, conclusion. So increased awareness about architecture and different issues which was not patched or patched badly. Another is software is supposed to use hardware really properly, meaning that we need to have a security guidelines for the BIOS configuration, for the SoC configuration, to making sure that all of the configuration set properly and have the mechanism to check that configuration. And x86 and ARM has a lot of similar vectors, and the architectures can teach each other to understand how to make security better. With this, I'm done.